Okay, awesome. So the topic that we're going to be covering today is basically going to be simplifying mathematics behind AI. Now, for a lot of people, maths can seem a bit complex. It can seem a bit daunting. And the reality is that behind a lot of your AI use cases and algorithms, there is going to be some maths, right? So our goal of this webinar today is to basically break down those concepts and try to understand them and simplify them. So just to go over my introduction again. So my name is Albert. I am a senior data scientist along with an instructor here at Data Science Dojo. So I have my academic foundation as a mathematics graduate, and I have also been participating in teaching various courses here at Data Science Dojo, including the Data Science Bootcamp and Python for Data Science. And while it comes to my hands-on experience, I work on cloud-based AI and machine learning projects. And the goal of that is to, of course, turn complex concepts into actionable insights for diverse audiences. Now, in our session today, uh, this is what the agenda is going to be. We will be covering pattern recognition in AI, and we will be understanding what role mathematics plays in AI. We will be learning how we can turn those patterns of AI into mathematical equations. We'll also be understanding some mathematical concepts such as regression and gradient descents. And we'll be touching upon calculus and linear algebra's use cases in AI. And then we will be looking at word and sentence embeddings and similarity metrics. So without further ado, let's go ahead and get started with our session for today. Now, AI or artificial intelligence is mainly based on pattern recognition. The goal of AI is to basically observe your data and identify any sort of underlying patterns or relationships that are present over there. For example, if you were to give it a picture of a cat, it's going to extract some information from that by recognizing those whiskers or those pointed ears. So the AI is basically recognizing some sort of shapes, edges, or objects with that use case. Or if you were to give it some text, it will try to find some sort of meaning and context from the words that are being used in that text. Right? So simply AI is basically all about finding those patterns. So you start off by giving it your raw data. That data is cleaned and pre-processed. And from that, some sort of information or features are extracted. And that basically is used to figure out what pattern is present within your data. Once that pattern has been uncovered, you can go ahead and start carrying out your analytics, or you can go ahead and start carrying out predictions. And these can assist a business in making some informed decisions. Now, here we have an example of a neural network, which basically is given an image, and the goal of that neural network is to take that image and extract some features from it. So basically, it goes through some layers, and after that, that image is simplified into a vector or a matrix. So what's happening over there is that there is some sort of pattern recognition happening. Now, our goal is to understand how we can take those patterns and represent it with a mathematical equation. So the role of mathematics in AI. Now, maths is very critical because it helps us in training the models, making predictions, and understanding different behaviors of AI system. And mainly, math can help you bridge the patterns and equations together. For example, if you were to see any sort of pattern present within your data. For example, if I was collecting my data of how much I watch YouTube videos, and I noticed some sort of pattern that at 9 p.m., I watch certain categories of videos. Now that's a pattern that I've observed, and I want to turn it into an equation and use that equation to make predictions about the future. And for doing that, maths comes into place. So there are different concepts of maths that actually help you out with AI. And that includes linear algebra and calculus. Now, linear algebra basically helps you convert those patterns into matrices, and calculus helps you optimize equations to improve pattern accuracy. So let's go ahead and dive into each of these in details and understand how does that actually happen. So for starters, in our journey of turning a pattern to an equation, Let's imagine a data set that consists information about different houses. And each houses will have a respective price. Let's take out one data point from our data set. This is basically a house that is 1,500 square feet and it has a cost of $300,000. We are going to treat this data point as a dot and we're going to try to plot it on a graph. Now, in this graph, what we are doing is we are assuming our x-axis to be the size of the house and our y-axis is the price of the house in $1,000. So if you were to take this data point, which was 1,500 square feet, and it cost $300,000, its mathematical representation is basically going to be x is 1,500 and y is going to be 300, which is basically $300,000. So if I were to plot this on a graph, you see this, the x value of 1,500, and this is the y value of 300. It shows up as a singular dot on our graph. So what we have done, we have taken one data point and we have mapped it onto this graph. Now we can repeat that process for different data points. So over here, we have a bunch of different houses. This house is 100 square feet and it costs $200,000. The next house, 1,200 square feet, cost $240,000, and so on. Each of these data points can be mapped onto this graph. Remembering that on our x-axis, which is this axis, we are plotting the house size, and on our y-axis, we are plotting the corresponding price. So going over each of these one by one, this house is 1,000 square feet and it cost $200,000. So price in $1,000 would be 200. So this will be our first data point. Now repeating this for the remainder of the data points. This house is 1,200 square feet, costs $240,000. So 240 and 1,200. This will be our next data point. And we can keep repeating that for the remainder of the data points. What we have done is basically, we have taken our data and we have represented it into a graph. Now, looking at this graph, there's going to be some sort of pattern that you're seeing. And that's a very simple pattern. The pattern that you're seeing over here is that as the house size increases, so does the price of the house. That means a bigger house is going to cost more. Now, the pattern that you're seeing over here can be represented with the help of a line. And this line basically suggests that there is a linear relationship between the size of the house and the price of the house. As the house size increases, so does the price. And we had all these different data points. And what we did, we basically created a line that passes through all those points. This is basically a linear relationship that we're representing with the help of this line. Now, we noticed this pattern in our data that as the house size was increasing, the price of the house was increasing. So what we did, we basically represented that with the help of a line. Now, going back to your high school pre-calculus, you would remember that lines can be represented with the help of some equations. So we notice this pattern, and now our goal is going to be to represent it with the help of an equation. So there are two things that we're going to be covering right now. One is going to be the slope of a line, and the second is going to be the intercept of a line. A slope of a line is basically how inclined that line is. Think about climbing up a mountain. If it's very steep, it's going to have a greater slope. And if not, it's going to have a lesser slope. So looking at all of these lines, this line is very inclined. That means it will have a greater slope. Then a line like this will have a lesser slope, and a line like this will have a lesser slope. So this is inclined, very inclined. This is inclined, but less than this. This one has no incline because it's just a flat line. And this one is in the opposite direction. So this is negatively inclined. Now, you can associate a number with all of these inclinations. So just for simplification purposes, let's assume that the slope of this line is 5. The slope of this line is 1. And since this has no slope, it's going to be 0. And since this goes in the opposite direction, it's going to be negative. Now that's the first thing, the slope of a line. The next thing is going to be the y-intercept, which basically means the place where the line cuts the y-axis. This is the y-axis, and that's the place the line cuts it. This is going to be your y-intercept. Now, the slope that we just talked about, that can be calculated with this formula, which basically is change in y divided by change in x. Change in y means how much y value changes, and change in x is basically how much your x value changes. So let's assume, with an example, this was what your equation was like. And you want to represent it with the help of the equation that we just talked about, which was y equals to mx plus c, where m is the slope of a line and c is where the line cuts the y-axis. So m is calculated by basically measuring change in y divided by change in x. And c is basically the y-intercept. So if you wanted to represent this equation, it would end up looking something like this, where you have this value as the change in y and this value as the change in x. So if you're going from this point to this point, your value of x changes by 500. And if you're going from this point to this point, your value y changes by 100. Right? So basically, just pick out any two random points from this graph and notice how x and y are changing. Going from 1000 to 1500, your x changes by 500. And going from 200 to 300, your y changes by 100. So if you wanted to calculate the value of m, that's basically going to be your change in y divided by change in x, which is 100 upon 500, which ends up giving you the value of 0.2. Now, that's the first part of your equation, m, y equals to 0.2x. The next thing is going to be the intercept, which basically means where does this equation, once you extrapolate it, cuts the y-axis. And over here, if you see, it cuts it at y equals to 0. So that's basically what your intercept is going to be. So putting all these values back into the equation, y equals to, your m value is 0.2, and your C value is 0. So you end up with this equation y equals to 0.2x. So as a recap, you started off with all these different house prices along with their sizes. And you've noticed that there was a pattern that as your house size increases, your price increases. And you ended up converting that into this simple equation. And what this equation does is that it lets you make predictions. If you were given the value of x, which basically means the size of the house, you could predict the value of y, which is going to be the price of the house. So you had on the x-axis, you had the size of house. And on the y-axis, you had the price of house. So for carrying this calculation out, what you will do is assume that you were given the size 2,000 square feet. All you have to do is multiply it with the slope. Putting this value over here, you end up with y as 400. That basically means if the size of your house was 2,000 square feet, your price of house will be $400,000. This multiplied by 1,000. Now, that's a simple case, right? This is the case of linear regression, where your equation can be simplified into a linear line. Whatever pattern that you're seeing is linear. Now, that might not always be the case. Your equations can be polynomial. And there are other cases that you can end up with. But for a simple case that we're talking about right now, what we did, we found a pattern and we basically turned it into this mathematical equation, which basically means that your price of house is equals to 0.2 times the size of house. And you can replicate this for other use cases as well. Now, calculating the gradient of a linear line is very easy, right? It's delta y upon delta x. But what about if the line was curved? How do you calculate the gradient in that case? What if I wanted to know what the slope was at this point? Or if I wanted to know what the slope was at this point? Looking at a linear line, the slope remains constant throughout. All you have to do is just do a delta y upon delta x, or you can do it over here as well, or you can do it over here as well. But what if the line was a slope? For that, what you do is you basically will build a line that's perpendicular to that point, parallel to that point, and you will measure the gradient of that. So if I were to build a line over here and I measure the gradient of that, that would be the gradient at that point. Let's understand this better with diving more into details about how calculus and AI works. So calculus is basically essential for understanding how AI model learns from data. And it helps us calculate changes and optimize models through mathematical functions. Now, previously, we were using this notation where we were calling the change in the value of x as delta x and the change in value of y as delta y. And this was one coordinate, x1, y1, and this was the other coordinate, x2, y2. Now, what we're going to do is we're going to just change this notation a bit. And instead of saying y, we're going to replace it with f of x, which basically means f is a function of x. So we're just renaming the notation. Everything else is the same. So instead of y, I'm saying f of x, and x remains the same. Now, for x, initially we had x1 and x2. What I'm going to do now is that instead of saying x2, I'm going to call it x plus delta x. Let me explain what that means. This was our value of x, and the difference between x and x1 and x2 was delta x. So instead of saying x1 and x2, what I'm just doing it that this is x, and since the distance between these 2 points is delta x, this value is going to be x plus delta x. So now this value is x plus delta x, and this value is x. So this value is going to be f of x, and this value is going to be f of x plus delta x, which basically means that f is a function of x, right? This was clear. So over here, it's simple. Now, the value of x is x plus delta x. It has increased slightly by this number. So we're going to replace this with x plus delta x. And this is the notation that we're going to use moving forward. Now, if I wanted to measure the gradient of this line, the concept is going to remain the same. It was change in y divided by change in x. What that means is that your y is changing by this much, and your x is changing by this much. So this is your value of y, the second one, and this is your value of y, the first one. So it's basically f of x plus delta x, this is the second value, minus f of x, which is the first value. And then we're dividing it by the change in the value of x, which is going to be delta x. And that's basically what the slope of this line is. Right? It's just the same thing as delta y upon delta x. We have just slightly changed that notation and represented it like this. Now, this is going to help us with calculating derivatives for the cases where the line is not a straight line. Over here, if you think about it, we had this curve, right? We cannot just simply use delta y upon delta x to calculate the gradient because the gradient at each point is different. The line at this point is like this, the line at this point is like this, then it just keeps getting flat. So the gradient is constantly changing. And to calculate the gradient at each point, we need to look at it a bit zoomed in. If we had a curve, if we were to zoom in for a brief period of time, it will just look like a straight line. Now let's apply that logic that we had talked about before over here, where the gradient was f of x plus delta x minus f of x divided by delta x. Now our goal is to make this distance as short as possible, to the point it approaches 0. What that means is that we are assuming that this change in x is getting very small. So the limit of delta x is basically approaching 0. And using that, we can calculate the gradient of the line at this point. Now, it's important to understand gradients because they have many use cases in AI. For starters, one second, let me just go to the... Okay, so for starters, what we're going to be covering is the importance of gradients in gradient descent, which is basically a way AI can use to improve itself. If you have any sort of model and you want to make it better, gradient descent can help you achieve that process. So going back to our example of linear regression, where we had this line. which was representing some sort of data. We had these house prices on the x-axis and prices on the y-axis. And over here, what happens is that you have these data points and you're trying to make a line that passes through most of them or find the best fit line. Now, in reality, data is not very clean. The pattern that you figured out, it's not going to be 100% accurate. There are going to be errors. It could be due to errors in measuring the data. It could be that the data does not follow an exact path. So there is going to be some sort of error in your prediction and your real data. So over here, we have these data points, and we also have this prediction that we're carrying out. And there is going to be some sort of error between the real value and the predicted value. Now, these errors can be represented with the help of some equations. And over here, we're going to be using something called mean square error, which is basically what we can use to figure out how good is our model or how bad is our model. We're basically calculating all these errors and we're summing them up together. And that's what basically a cost function is. A cost function is how AI measures how wrong it is. Think about it as a scorecard that basically tells you how far is the model's guesses from the actual answers. For example, if a model predicts 3 and the actual value is 5, there's this distance of 2 between the real value and the predicted value. That is represented with the help of cost function. And our goal is to basically minimize this cost function as much as possible. We want to make this value as small as possible. Minimize the error within our data. And for achieving that, gradient descent comes into place. What it does is that it helps you figure out at what point is your cost the minimum. So over here, we have this cost function, right? That cost function can be presented in a graph. And it will, let's assume it looks something like this. Now, in this cost function, we have this point, which is called the minima. And at this point is your error the least. And what you're trying to do is you're trying to reach this point. You want to minimize your error as much as possible. In your model, there is going to be some error, and you want to figure out how can we reach this point? How can we minimize this cost function? There are going to be some parameters that you want to play around with to end up reaching that point. And for doing that, gradient descent works. So you have this cost function that's covered in orange color. And you want to, whichever point you start from, you want to end up reaching this point, which has the minimum cost function. And for doing that, you will be using something called the derivative of that line. So at each point, you will have a derivative of that line, which is basically the gradient of that line. So for example, over here, the gradient is, let's start from the right-hand side. That's going to be much easier. The gradient is a lot. Then the slope is decreasing, decreasing, decreasing till it gets flat, which means the gradient over here is going to be 0. Over here, it's the most, let's say 5, then 4, 3, 2, up until it reaches 0. While over here, it's in the opposite direction. So the gradient is going to be negative. It's -1, -2, -3, -4, and -5. Now, whichever point you start from, you want to go from that point up until this point. Now, how do you figure that out? How do you know, should I go towards this side or should I go towards this side? Well, the derivative helps you achieve that process. Basically, we just talked about how we calculate those derivatives of these lines, right? We basically are going to build a parallel line and we will calculate its slope or its gradient. Remembering that the gradient over here is negative and the gradient over here is positive. So how does the model know should it take a step in the right-hand direction or the left-hand direction? Well, if it's positive, if the gradient is positive, it knows to move towards the left. So if the slope of the line is positive, go towards this direction. And if the slope of the line is negative, go towards this direction. So if you were to start from this point as an example, it will first figure out what the gradient of the line is at that point. And over here, since it's positive, it knows to take a step in this direction and it will move further. And it will keep doing that until the gradient becomes 0. Remembering that a slope of a line like this is 0. So this is the part where your cost is minimum. This means this is the cost where you are reaching the least error associated with your model. So your goal is to reach that point. And with the help of the gradient descent, you can figure out what the optimal point is. And using that, that will give you your optimal weights for your machine learning model. So think of it as like rolling a ball down the hill. It finds the lowest point. And yeah, that's basically all about gradient descent. Now, moving on, we're going to be covering the next topic, which is going to be linear algebra. And linear algebra in AI is basically the foundation of many algorithms in data science, especially those involving data transformation and optimization. So there is a huge boom in the generative AI field. LLMs and generative AI is at the very peak right now. ChatGPT and Bard and all these other models. At the back end, they are making use of linear algebra, which is why we're going to be taking the remainder of the session to understand how linear algebra works and how they work in different machine learning algorithms. So for starters, the first concept that we're going to be covering is going to be vectors. And vectors basically represent data points as coordinates in multidimensional space. So let's say that we have a vector A, which is 2, 1. And we have another vector, which is B, 5, 2. So basically, think about these as individual points going from your point of 0, 0. And that's going to be your vector A. And then we have the second vector B5, 2, which is going from 0. That's your vector B. So basically, the goal of vectors is to represent your data points in dimensional space. Now, here you have I'm restarting my screen share. Okay, so we were talking about vectors, and the next thing that we wanted to cover was going to be vector addition. Let's say you have this vector A, which has the points 2, 2, 5, 6, 8, 9, and B, which has the point 5, 2, 6, 5, 1. Now, if you want to add those two vectors together, A, which is something like this, and then B, which is, let's assuming something like this, and you want to add those two vectors together to get A plus B, the calculation goes something like this. You have each of these individual values added together one by one. So these first two values get added together, then these next two values, then these next two values, then these next two values, and then these final two values. So if you want to add A plus B, it's going to be 2 plus 5, 2 plus 2, 6 plus 6, 8 plus 5, and 9 plus 1. That is 7, 4, 12, 13, and 10. So the sum of these two vectors is basically 7, 4, 12, 13, 10. Now, why are we talking about vector addition? Why are we talking about vectors? Well, that is to come in the later slides when we start diving into how embeddings work and how are they used to create your generative AI models and so on. Before that, let's talk about something else, which is matrices. So your AI relies heavily on vectors and also on your matrices. Your vectors were basically just your simple vectors. Now matrices, it adds up into a grid of numbers. Previously, you only had a single list of numbers. With matrices, it's going to be a grid. And matrices can be used to represent your data and inputs and outputs like this. For example, assume that you had an image of this number 5 in black and white. And you wanted the machine to be able to use it and interpret it and make use of in your machine learning models. How would you go ahead and do that? How can the machine understand this image? At the moment, it's basically your raw data or your model that you're building, whatever AI tool that you're using. They will not be able to understand it until you transform it into a form of numbers. And you can achieve that by converting it into a matrix representation. And how does that work? Well, think of this box as a 7x6 matrix. And each pixel will represent one color. Right? So let's build this box quickly. And over here, this box is completely white. This box is also completely white. This box is also completely white. All of these are completely white. So what we're going to do is we're going to use this representation where white is represented by 0. And something that's completely black is represented by 255. So your numbers over here are going to be 0, 0, 0, 0, 0, and 0. This is also 0, but over here, this box is completely black. So this will get the number 255. Similarly, this will also get the number 255, 255. This box is slightly gray, so it's more towards white and less towards black. So it's really something like, let's say 50, depending on how the intensity of the black color is. And this is again white, so that's 0. And that will repeat for the entirety of the image. So this is something like 50. This is 0, 0, 0. This might be something like 20. This is also something like 20. All of these blacks are 255s, and all these whites are zeros. So what you have done is you have basically taken this image and you have now converted into this 7x6 matrix, where you have all these 7 values over here, and you have these 6 values over here. Now, once you have your data converted into a matrix format, you can then pass it to the machine and it will be able to interpret it. And it can apply different processing and calculations on top of it. Now, we do the same thing for text data as well. And that's what goes behind large language models, which is taking your text data and converting it into some sort of numerical format. And this is achieved with the help of word embeddings. So word embeddings are basically words being mapped to some sort of vector space based on their meaning. And the goal of these embeddings is to basically capture semantic relationship between different words. Like words like king and queen, they're very similar to each other. And they're not going to be very similar to apple. So once you create those embeddings, king and queen are going to have similar representation than apple. So in mathematics, if you were to take an example, something like cat would then be mapped to something like 0.12, negative 0.34, 2.5, 3.7, and 1.9. This is just a random example. And you might be wondering, where do these numbers come from? Well, these numbers are extracted with the help of neural networks. And what they do is they try to find what sort of pattern is present within your data. So words that are appearing together, such as dog and pet, will have similar vector representation. And that's because in a document where somebody says, I have a dog, they will also say that I pet my dog or something like that. Similarly, if a document is talking about king, it might also talk about queen. So words that occur together, they end up having similar vector representation. That means that they are closer to each other. So if it's, what do you mean by similar? Well, if it says 0, 0, 0.5, and 1, this will have similar values. 0, 0, maybe something like 0.55 and 0.91. These two values are very close to each other, and these two values are very close to each other, and these two values are the same. So basically, what it does is that it uses the information of words occurring together to generate these embeddings, and the values are. So that's what happens over here with your word embeddings. Now, models like Word2Vec, what you do is you feed them large amount of text documents, and what they do is they automatically extract those patterns present within those text documents. Or basically, let's say if you feed it a lot of English documents, it will try to figure out how similar are different words in English language to each other. They might be used interchangeably. So they will, these words, since they're occurring together, they, sorry, I think my voice was breaking up. So let me repeat. So words that occur together and words that are similar to each other, they will end up having similar representation. So that's how what we do. We take those text words and we come up with this mathematical representation for it. Now, why is this important? Well, for starters, this sentence consists of 6 different words. And each of these will end up having some sort of vector representation. For simplification purposes, let's assume that the has the number 0.1, 0.2, 0.3. Cat has this number sat on the map. Right? So this sentence, each of the word has this respective representation. Now, if you want to see how can we represent this entire sentence mathematically, we would have to combine all these numbers together somehow. And for doing that, what you can do is you can take an average of the vectors for the sentence. So you have this word sentence, the cat sat on the mat, and you have all the individual numbers for those vectors. So if you go back, all of these are here. And I want to see how can I represent this entire sentence with the help of a vector? Well, I will take these unique representation, add them up together. So these all added together will give me one value. These all added up together will give me one value. And these all added up together will give me another value. Since I have a total of 1, 2, 3, 4, 5, 6, 6 words, I'm going to divide it by 6. So as an example, let's do this. 0.1, 0.5, 0.2, 0.3, 0.1, and 0.6. Adding them all up together, divided by 6, we will end up getting the average value. So for example, we have this cat sat on a mat. This will be averaged out into a value something like 0.338, 0.56, and 0.3. So that's what we did right now. We represented one sentence, right? So if we had a bunch of documents, we can represent each of those documents into their respective representation. Now, how does this help us converting documents into these embeddings? It lets us apply a lot of different machine learning algorithms. For starters, we can see which article is most similar to another article. We took an article, we calculated the individual word embeddings, and then the combined embedding average, and it looks something like this. And now I want to see which other article is this the most similar to. So for doing that, we have these similarity matrix. So let's talk about cosine similarity, which basically tells us how similar is one document to the other. So if I go back, what I've done is I've taken my document and I've represented as a point. Another document again as a point, and another document as another point. And this distances between these points basically tells me how similar are these documents to each other. If it's very further apart, that means it's less similar. And if it's closer together, it means it's more similar. So if this distance is short, that means the document is very similar. And if the distance is large, it means those two documents are not very similar. Now, the distances can be calculated using different formulas. One of them is Euclidean distance, which looks something like this: x2 minus x1 plus y2 minus y1, which basically means we subtract this from this, their x values, and then we subtract the y values. So as an example, let's just do one quickly. Let's say that we have this point 3, 0, and we have this point 0, 1. This is x1, this is x2, this is y1, this is y2. And if you were to measure the distance, it's going to be 3 minus 0 squared plus 0 minus 1 whole squared. And this becomes 9 minus 9 plus 1. That's the under root of 10. That's the distance between this. Now, if this was under root 10 and this was under root 51, we know that this distance is much larger. So this document is not very similar to this document, but it is very similar to this document because this distance is much shorter. Now, this distance can also be calculated using cosine similarity, which basically tells you, which is another metric to figure out how similar are documents to each other. Now, the formula for that is basically written over here. And it basically, rather than seeing the distance, it sees the angle between points. So if the angle is shorter, let's say that this was one vector, this was the other vector, and this was the third vector. This angle is shorter. That means A and B are more similar. This angle is much bigger. That means A and C are less similar. Now, you can learn more about these similarity metrics by Googling them and how you can calculate them. Since we are short of time, I would like to allot some time to the questions that anyone might have. So this would be a good point to wrap up our session. And I hope this session was very helpful to all of you as a starting point for understanding how mathematics can be implemented into different domains of AI. I will now open the forum to different questions that anyone might have so that we can address them quickly. All right, so let me just go through the chat. I'm just going through the chat, just give me a minute. Okay, so there was one question about the data is not that messy, thus the cost function is not necessarily smooth, but quite bumpy and chaotic. Okay, so it could be, so the cost function is basically an equation that you create yourself, right? So you figure that out with the help of the data that you had. In our use case, these were just sample visualizations and graphs. They were not based on real life data. So it might be that at one point it could be not matching the other one. This was just for explanation purposes. So yeah, I hope that addresses your question. Let me just go through the chat for other questions. Okay, so there is one question about how do we apply this in coding. So um, this was basically the goal of understanding how these different models work, right? What is happening at the back end of these models. When it comes to coding, all the mathematics has already been done for you majority of the times. The models that exist have all these things already written for you, and sometimes it's pretty much as simple as just writing just one line of code that does your task for you. However, it's very important that you also understand what's happening at the back end. Because if you were to use a model without having any information about it, you might end up picking the wrong model in the wrong scenario, right? So the goal of this session is to understand what happens at the back end of AI. For implementing all of this in activities in coding, there are numerous resources available out there for Python. There are also drag and drop models available out there. Um, so yeah, this was what the goal was, right? And can you recommend any simple tools for experimenting with creating simple models? So if you want to if you don't want to dive into much about coding, there are methods available which have a drag and drop interface where you're actually not writing the code. All you're doing is just dragging and dropping and using the tools as is. For example, Azure Machine Learning Studio, it provides you the opportunity for carrying that out. But for if you want to dive into more about coding, my personal preference is Python. Some people prefer using R. There are, again, numerous resources available on the web for that, for creating the models from scratch or using existing libraries. In Python, sklearn has all these different libraries that allow you to carry out different sort of machine learning models, building, and all of that. So yeah, hopefully that addresses your question. So there is a question. So one needs to know calculus, linear algebra, and statics and probability to understand machine learning better. Is there a sequence one should follow to learn these math topic? So I would say there is no exact sequence that you would need to follow. Calculus. So these are covering some of the concepts and areas where these come into play in AI and machine learning. Right? It actually goes beyond that. It has many other use cases. I would say that we have only touched the tip of the iceberg. It was a very introductory section. There are other areas as well where these mathematical concepts come into place, right? Sorry. So calculus, linear algebra, and statistics and probability, these are the things that actually are used in AI and data science throughout each and every single domain that you will come across in different or various ways. So there is no exact sequence that you should follow. It's recommended that you know all of these, so you can understand how exactly is your machine learning model working or your AI model working. It's good to know the theory behind what's exactly happening. So in case if you run into any errors or issues, you can debug it and improve the model further and get to a better solution. So yeah, hopefully that addresses your question. So there is a question about explaining mini batch and stochastic gradient descents in the context of epochs. So that would be an entire webinar on its own because it's a very detailed topic. But I would suggest that going to a tutorial that you can make use of and understanding this better. All right, that sounds good. Thank you, Sandra. Yeah, so I guess that is all the questions. Nabi, have you got any questions?